Yeah, we understood.
It's like a midnight for me, but though it is still 9 a.m. But thank you very much for organizing this, and also thanks. Just 1 minute. I'm just looking at my presentation. Okay. So okay, let me
Okay, sir.
share the screen.
Yeah,
Yeah, go ahead.
kindly allow me for the formal introduction, sir.
Yeah, sure, of course. Go ahead. That's perfectly fine, no problem. Yeah.
So on behalf of Hindustan College of Engineering and Technology and Department of Aeronautical Engineering, we welcome Dr. Anusuya Ponnusami, our today's resource person for the 5-day FDP program in advancements in aerospace materials, manufacturing, testing, and characterization. We welcome you, sir. May I request Ms. Diksha Sambyal to give the brief introduction about our today's guest speaker. Over to Diksha.
Very good afternoon, everyone. It's my privilege to introduce you all to today's guest of honor, Dr. Sathiskumar Anusuya Ponnusami. So he is working as a lecturer in structural mechanics in the Department of Mechanical Engineering and Aeronautics at City University of London since October 2018. Prior to the City, he worked as a postdoctoral researcher in solid mechanics and materials engineering at the University of Oxford, where he also continues to be a visiting academic. He also serves as the deputy admission tutor for undergraduate engineering programs at City University of London. He graduated with his PhD from the Delft University of Technology in Netherlands. His doctoral research centered around computational modeling of fracture and healing in self-healing turbine composites coating for aerospace applications supported by collaborative experimental development with material scientists. He also served as the leader of the team multi-fund that won $30,000 Airbus UNESCO Fly Your Ideas Global Challenge 2015. He's also the awardee of the NLF Dutch Aerospace Award 2015 University category Netherlands, ITMA Future Materials Award 2015 WTIN UK, and ICHM Young Scientist Award 2013. Some of his current research topics include application of data-driven and machine learning techniques to structural mechanics and material problems, multi-physics modeling of multifunctional heterogeneous materials, integrated numerical experimental modeling for mechanics of composite materials, multi-scale homogenization and failure prediction, reduced order structural models. Thank you so much, sir, for sparing out time from your busy schedule and joining us today. We are so grateful to you, and I hope we'll all get to learn a lot of things from you. Thank you.
Oh, yes. You have your great, thank you. Okay, thank you very much, and thanks for the sweet introduction. And I think thank Chori Gopi, who was my senior during my university days back in my bachelor's. I hope he's available here. Is he? Or he's
yes.
Hi, Gopi. Good. Thank you. Okay, great. So let me start the presentation without spending time on other things quickly. So today I have a too little presentation, and I see that I'm allotted for about 90 minutes if I'm not wrong. But I promise that I won't take too much time, the entire 90 minutes. So let us try to make it a bit interesting, and then let me share the screen and share some of my recent research activities in the domain of artificial intelligence and multifunctional materials for aerospace applications. Okay, so before going into it, I hope you all can see me. Why I have chosen these two topics for this presentation, in particular, the applications of artificial intelligence and the scope of multifunctional composites for aerospace applications again. So the primary reason is that,
Excuse me, sir.
yes, can
Your
you hear me?
yeah, your screen is not yet shared. In case
Oh yeah,
we
it is not shared. It is not
all
shared
right,
yet.
all right.
Yeah,
Thank you.
no worries, no worries. I'm still in the beginning phase, so I'll share it once I wanted to. Don't worry. Thank you. Okay, so again coming back to the topics. First on the multifunctional materials. Why multifunctional materials in general, especially in aerospace industry, is that aerospace structural and material industry is unique as compared to the other industries, say civil engineering or nuclear engineering, or even mechanical engineering industry. And why is that? Because as aerospace engineer, we strive to focus on two specific things. Yeah, of course, the design of an airplane, but within that, there are two things that are really important. The first one is the weight, and the second, the space. Yeah, so apart from the structural superiority in terms of the strength stiffness. So this weight and the space are two crucial factors if you think about it. Yeah, which is not the case if you build something, a building or any other ground-based machineries in mechanical engineering. That is not the case. And the reason why these two factors, the space and weight, is important or important is that you need to lift the airplane up, isn't it? And you need to hold the people, the passengers. And for these two reasons, these two design factors are crucial. With the current techniques in the materials development, which is predominantly composites in aerospace industry, if you take A380, more than 50% of the aircraft structure is composite. You take A350 or Boeing 787 Dreamliner, you always have composites, more than 50% of the aircraft weight, isn't it? But can we move forward? Again, with the context of saving space and weight, can we move forward? The answer is it's not that straightforward, because the advancement in composites have saturated. We have made the airplane lighter and lighter and stronger and stronger. Yeah, so we have reached the threshold. So to push it forward, one of the promising scope or options that we have is to introduce the so-called multifunctionality into the structures. And what do I mean by that is, in simple words, you make a structure that does more than one function. Yeah, like human skin, it does n number of functions, isn't it? Apart from protecting our internal organs, it does many different things. The same thing. Yeah. So imagine you have an aircraft wing structure. Currently, what does it do? It takes the structural weight, isn't it? And it produces the lift aerodynamically, and structurally it holds the weight of the airplane. Yeah, it does the structural load bearing. That is the primary purpose, which is not enough when we talk about multifunctional composites. We want to incorporate more and more functionalities into that. Okay, so that without adding weight, without adding further weight or space, consuming more space, we have more functionalities. And that has a direct implication on what? On the space and weight, isn't it? Which means the fuel consumption and hence the efficiency. And in the end, ultimately, we are leading to sustainable aviation, isn't it? Yeah, so that is the rationale of bringing in the multifunctional aspects in today's presentation. And I'll share my screen on, let's say, 20 minutes of my talk focusing on multifunctionalities in aerospace. And after that, let us move on to the scope and the potential of AI or machine learning or deep learning techniques for aerospace structures and materials. Yeah, so let me share the screen. Okay. Okay, can you all see the screen? I hope yes, yeah?
Yes, yes.
Okay, perfect. Okay, so the title that I've given is very similar to what it is here. It's basically focusing on two different topics, and so whatever that I'm presenting, those are the research activities that have been done in different institutes. At Oxford, at TU Delft, and IISc, where I studied my master's, and then also the current institute, which is the City University of London. I'm not sure if any of you have heard about City University of London, but to give you an idea, it's in central London and in the UK. And to give a name, it's Mahatma Gandhi who actually did his law degree at this university, exactly in the same building that I sit at, not right now, but in my office. Okay, I'm currently at my home giving this presentation. Okay, and it's part of the big University of London, in which there are more than 7-8 different universities, including University College London, Queen Mary, and so on. Okay, so coming back to the topic, my research experience generally spans across 3 different areas on analytical methods for aerospace structures, and then computational techniques to analyze and design aerospace structures and materials, but also some experimental investigations of advanced composites through experimental testing, especially under fracture and damage by impact loadings. Okay, I don't know why the date is not changed. I changed it here, but it didn't change here. But please ignore that. This is also one of the presentation that I gave earlier. Okay, so on the multifunctional composites, what you see here is one of the first topic that I worked in the context of multifunctional materials, and the title is Self-Healing Gas Turbine Coatings. And I was part of this project as the core researcher when I was at TU Delft, and then it's part of the bigger EU project, European Union project, in which many universities and industrial partners are involved. You can see some of the familiar names, Manchester, NLR, Alstom, which is now called GE, engines, and so on. Okay, but let us go into the actual topic. Of course, you all very well know an airplane, and one of the core components of an airplane is the jet engine, isn't it? Yeah, as you can see schematically, the different components of a jet engine would start with the compressor, and then the usual the components, including the combustion chamber, turbulent, and the nozzle, isn't it? So if you look at it here, the color codes basically tells you the temperature distribution, and the more red means the temperature is high, and the typical operating temperature is around 2000 to 2500 degrees Celsius in the turbine sections. But of course, all of you would know these turbine blades are made of advanced metallic alloys, primarily from nickel-based alloys, yeah, which can handle very good temperature, but not 2000 degrees. Yeah. So what we usually do is that we have this high-strength alloys, but on top of it, to withstand such very high temperatures, we basically coat these nickel blade alloys with ceramic coatings, and we call them as thermal barrier coatings. Yeah, as you can see here, this is your blade, a typical nickel alloy blade, and on top of it we have a coating, and the microstructural picture of the coating is what you see here. Yeah, so as you can decipher from the top right image of the microstructure, you have different layers there. Yeah, it's a single coating, but it's more of a hybrid coating. So you have a blade underneath, that's the metallic blade, and on top of it you have the so-called bond coat, as you can see here, if you can see my mouse pointer. So the bond coat is a metallic layer again that is used to bond the underlying metallic blade to the ceramic coat on the top, and that ceramic coat is a top coat. It can go up to. Okay, and why am I showing this picture is that this particular microstructure shows you a coating layer which is made of both metallic and ceramic constituents. Yeah, so imagine you have a metal and then a rubber layer bonded together, and you put it in the oven, you heat it up. What happens? Because the two materials that are bonded together are of different different, let's say, characteristics, one expanding more than the other, naturally what happens? You develop thermal stresses, isn't it? Because both of them are bonded together, but one of them tries to expand more than the other. So you naturally develop the so-called thermal stresses. And those thermal stresses during operation, meaning every takeoff and landing, those stresses create cracks, micro cracks. And that is what you would see in the next slide. Yeah. So that is a schematic of the thermal barrier coating. We call it as TBC. Yeah. And you see little micro cracks there. And that is created due to the thermal stresses. And during operation, you see a little black line in the middle, if you can. So that little black line is basically called as an oxide layer, which grows continuously during the engine operation, meaning every takeoff and landing, the thickness of that particular black layer, the oxide layer, keeps growing. Okay, but if it keeps growing, what happens? You are adding additional heterogeneity into the structure, which means the stresses would be more and more, which means the micro cracks would become more and more. But in the end, if you leave the micro cracks to form and grow, ultimately all these micro cracks, they coalesce, and then they form a major crack, which leads to the entire failure of the blade, not the blade, but the coating. Yeah, and which we call it spallation. So the blade coatings, or rather not us, what the aeronautical industry do, mainly the MROs, whether it is the operators or the companies who make the engines, they replace the coatings. Yeah, they take the engine out, they clear the remaining bits and pieces of the coating, and then they recoat it. And that process is extremely costly. Okay, and what is the other way to go? Of course, you can try to improve the coating by techniques, manufacturing techniques, introducing new different materials for coatings and so on. But then you are not able to prevent the damage, isn't it? Because you need to fly, which means you will create stresses, which means you will cracks. Okay, so that is unavoidable. So what we actually proposed in this particular project, which is of about 5 years of research worth 5 million euros during that time between 2012 to 2017. What we did is we posed the following that you see on the right. And you see the little particles over there with a red color boundary. Yeah, so and those are called healing particles. Yeah, and these healing particles, what it does is that when the micro cracks happen, yeah, which meaning when the flight is in operation and then when it lands, thermal stresses leads to crack, and when these crack interact with the healing particles, what happens is that these cracks open the particle. And once it opens the particle contains specific healing agent. Yeah, and that healing agent diffuses through the crack. And through further oxidation, it heals the crack. Thereby, you regain the structural integrity. Okay. So what you are effectively doing is that you see the blue-colored healed cracks. You are not allowing the micro cracks to coalesce, meaning to join together to form a major crack, as you see on the left. So, and by doing it, see, remember here, the important point here is you are not preventing any crack to form, because that is unavoidable. Cracks do form, but what we are trying to do is that we try to heal all those little micro cracks and prevent the formation of a major crack. And by doing it, you basically enhance the lifetime. Okay, and through our experimental testing with computational design, we were able to achieve a 30% increase in the lifetime of the thermal barrier coatings. Okay, and that is quite significant. 30% might seem a bit little, but it is quite significant for the aeronautical industry, because these maintenance operations, or rather repair operations, are not only costly, but also have downtime, engine downtime. You cannot fly, of course, without the engine, isn't it? So it all adds to easily several hundreds of thousands of pounds or euros, depending upon where you are in, for each carrier. And if you add that to the entire world, you can calculate the amount of cost and time, human time, and downtime as well, for the aeronautical industry. So now this structure or this material is clearly multifunctional. More thing, it heals itself. Yeah, when the structure or the material cracks, it heals itself and regain its original load carrying capability. And that is the additional functionality that we add into this particular system, which is not there before. And without adding more weight and side, and natural questions would arise. Some of them would be, okay, you are adding foreign particles into this existing structure. Wouldn't it weaken the system? Yeah, a natural question would, because these particles looks like foreign objects for this original system. Wouldn't it affect the original structural integrity? Yes, the answer is yes, it could be. But that is why we need to do the research to see how effective is it. So what is the cost effectiveness that we achieve through this? Okay, great. The other obvious question is, okay, we have these nice healing particles. When the crack forms, what if the crack goes away from the particle instead of being attracted towards it? That is also a beautiful difficulty, isn't it? Imagine the crack goes away from the particle instead of hitting the particle, the healing particle. Then the entire concept is a failure, isn't it? Yeah. So all these challenges have been addressed through the research, and we were able to achieve a configuration, an optimal configuration, in which you do not degrade the original properties of the system, yeah, but also you do not add additional weight into the system. Yeah, that is number two. And the other thing is you make sure the healing is activated when sufficient microcracks are formed, and we make sure they approach towards the particle. And that is done through an experimental computational approach, integrated, whereby we develop design guidelines on what particles to choose, what should be the size of the particles, what should be the shape of the particles, where they should be dispersed during the manufacturing process. Is it close to the interface or somewhere else? What should be the distribution? How many particles should we put in? So all these questions are addressed through the integrated approach, whereby we derive computational guidelines and do experiments with the computational models. Okay, so that is the whole crux of this particular concept. Of course, I do not want to dwell into the details of the research, and if I can not skip, but take you through some of the research results. As I talked about as you can see, the first challenge is, if you see the case A and case B, you clearly see case A is what we need, yeah, for the healing to work. Whereas case B is something that we do not want because the crack deflects. And in that case, healing would not happen. But now, the interesting point here is, in traditional composites, and traditional fiber composites or particulate composites that we typically use in aerospace, as well as automotive and wind energy industry, wind turbine blades, we actually would like to see case B to happen. And why is that? I'm not sure if this session can be interactive, but nonetheless, in the context of composites, why is that so? Because crack deflection is one of the strengthening mechanisms. Yeah, it's one of the toughening mechanisms for composite materials. But in this particular application, we do not want it. We do not want strengthening or toughening. We want the particles, the healing particles, to break. Because remember, the purpose of the healing particle is not to strengthen or toughen the structure, the original structure or material, rather to introduce the healing functionality. Okay, so that we make sure that case A happens, and that is through a series of parametric studies, both experimental and numerical, to choose the right type of particle in terms of its properties. Okay, great. And the second requirement is, as I already discussed, the introduction of healing particles should not deteriorate the original mechanical properties. Yeah, obvious requirement, because you introduce something new, and then what if you lose the already existing properties? That is not really advantageous. So that is another challenge. And the third challenge generally is that once the system, this particular proposal or the idea is developed and matured, we need to have a computational model or tool to analyze these kind of systems. because as you would all know, we do have a range of tools to analyze fracture or damage in structures, but we do not have tools to analyze healing. Healing is the reverse of damage, isn't it? Reverse of fracture. And for that, the physical models are not that much available, either in open source or in commercial tools. So the research also encompasses a part in which we develop computational tools to analyze these kind of new mechanisms. Okay, so that is the part on multifunctional materials. And first part, let me quickly, without going into the details of the results, because I want to cover a few more topics, is the second part of the multifunctional materials or composites is what I'm going to show in this particular animation, which I was introduced with this particular let's say characteristic of mine. So during 2015-16, we participated in Airbus competition. Some of you might be aware. It's the fly your ideas, and the concept that actually won the first prize. Of course, it's not only hard work but also luck plays, isn't it? Because we have more than 500 teams participating from more than 100 countries, and then you have to go through 3 different rounds and finally win with the first place. Is not just hard work, but hard work, of course, not needed. But it's also about how you present things, how you communicate things. It all matters. So it's not just the idea alone, but also other things, how you package things, which is important. Yeah, one is to do some excellent research. The other one is how you disseminate the research, not only to the technical audience, but also to the general audience. So both are equally important. That is also the case in teaching. Yeah. So it's not about how good you are in the technical knowledge, but also how good you communicate, isn't it? And research and teaching doesn't necessarily have to be the same. I mean, one person can be really good at research, and some other person can be really good at teaching. So it's a unique skill that we all need to develop as academics, to blend these two, let's say, entirely different skills together, so that the students can benefit at large. Okay, now coming back, I tend to shift from the topic that is not really relevant. Just a quick question. Do we have students as well in the audience, or we are all academics only?
No, all of them are mostly 99% academicians, research scholars, and some of them from industries.
Okay, perfect. That's good to know. Okay, thank you. Okay, great. So all of you are all colleagues in academics. So that is why. So that means whatever that I spoke before, it's all relevant, I believe. And some of you may be my seniors, as you can see. Gopinath was my senior long back, and yes, we have good touch with our seniors, and it always helps. And I came from a humble background, as many of you are, and I have to say is that if you have the passion and let's say the motivation to do some nice things, of course, you will be able to do. And I've been in some really good institutions in the Europe, from TU Delft to Oxford, and currently at City. So what I'm trying to say is that after this talk, if you have any questions or advice that you would need, feel free to get in touch, and I'll try to see if I can help in ways possible. I cannot guarantee that I can get you what you want, but I can guide you in the directions that you would want in terms of teaching, or in terms of research, or any further prospects. Okay, so coming back to multifunctional materials, this particular animation is the project. It's not done by me, it's by the team, in which I happen to lead the team, but it is a team of very bright students at that time, from different universities, from UK, from the Netherlands, from the US, and from India as well. And the mentor was Professor Sathiskumar at the Indian Institute of Science, the academic mentor, and I led the team. So the idea here is that you have a nice airplane, which is the schematic or the video that we prepared for the presentation to Airbus. So what you have is an airplane, and imagine you are sitting in the near the window. Yeah, imagine you got the window seat. So if you pop through the window, what you actually see is the one that is going to come. The wing vibrations, isn't it? So wing vibrations is something that is unavoidable because aircraft is flying through the air with turbulence is normal, which means vibrations are normal. You cannot avoid it. Yeah. So, but what we can do is that we can make use of these vibrations in a positive way, and that is the core of this project actually. Yeah. So what we actually did, we replaced the existing carbon composite panels, yeah, carbon fibers basically, and then replaced these carbon fibers with two different multifunctional fibers. Okay, and one of the first fibers is the piezo fibers. The other fibers are battery fibers. Okay, and we put them back together into the wing. And in the end, what you have is when the wing vibrates, you harvest or recycle electrical energy from the vibrations and store it in the adjacent battery panel. Okay, so simultaneously, what you're trying to achieve here is an aircraft wing that originally handled the loads, but now recycles and also importantly stores energy. So thereby your aircraft wing is doing three different jobs, three different functions, and that is a true multifunctional structure, isn't it? Yeah. And of course this project, if I want to give a presentation on just this project, that would take easily a couple of hours. But without getting into the details, what we tried to achieve is the design of a multifunctional wing and fuselage such that this multifunctional structure does three different functions, meaning the load bearing, which implicitly means that the strength and stiffness of the existing structure is not compromised. Yeah, and then we made sure it harvests or it recycles the maximum possible electrical energy from the vibrations. Yeah, and the third one is we also made sure it stores sufficient all the recycled energy into its structure. Thereby, your structure is a battery as well. It's a harvester and a load bearer. Okay, and that is the beauty. And why is this important? This particular topic or the concept is important, especially for the sustainable aviation or the future of aviation. All of you would know about Tesla, but all of the companies are now making electric vehicles, not airplanes, electric automotive cars. Yeah, for obvious reasons. Yeah, so basically to enable greener transportation and sustainable transportation, to reduce CO2 emissions, thereby the climate change can be mitigated, isn't it? That is the whole purpose. But aviation is slightly lagging behind for obvious reasons, because automotive cars, it's good, you carry the battery, it's all in the ground. If the battery is drained, you recharge it in a not fuel station, but a charging station, and you go. But even in the automotive cars, one of the major hurdles for the automotive manufacturers is exactly this, isn't it? The battery capacity. Yeah, if it is a petrol or diesel vehicle, it's quite easy. You have established fuel stations, and even one tank full would take you really to the destination that you really want. Yeah, but for an electric cars, the range or the endurance, as we call it in the aerospace context, is really limited. Yeah, and there is a significant amount of research that has been done in the automotive sector as well, or in general the material structure or the battery sector, to enhance the specific energy density and the specific power density of batteries. Okay, and of course these days lithium-ion batteries are quite popular for obvious reasons. Okay, but in the aerospace sector, it's not that you have to move the plane forward, but also you need to lift the airplane up. Yeah, and that's a challenge, isn't it? So there are two different work or energy that you need to spend. One is taking up in the sky, the other one is moving forward, which is given by your engine as well. So for this, and also the space is quite limited, which means, and also you need to have as minimum weight as possible. Yeah. For example, take one of the example of Airbus airplane, the demonstrator called E-Fan. Yeah. It can carry up to 4 passengers. Yeah. And in one full charge of that particular aircraft, it can go from London to Paris, and that's all. If it has to return back, you need to recharge it again. That is not the case in the typical airplane, isn't it? Take any regional transport airplanes, yeah, from ATR, or take, for example, A320. from Chennai to Madurai, if I want to go, or Chennai to Bangalore, doesn't matter. It can do multiple rounds, isn't it, without refueling. But that is not the case with electric airplanes. The only possibility is that you have to take more battery, but more battery means more weight. That means you are again going back into the loop. So the only way possible is that, can you have more battery capacity without adding weight and space? And this particular concept would be the ideal solution, isn't it? Because now, with this concept, if designed properly, you're converting your existing wing structure and fuselage structure into a battery without adding weight and space. Because wings and fuselage are anyway there. They are present. Yeah, you can't fly without the fuselage and the wing, isn't it? Yeah. So you're doubling, rather tripling up the existing structure to carry more energy without adding weight and space. And that means you can enhance, possibly increase the range and endurance by 50%. We showed in this project that we could enhance or increase the range of an electric planes by 50%. And that is quite significant, quite significant. In other words, an airplane developed by Airbus, if it flies for 1,000 miles or 1,000 kilometers, with this particular concept, it can go in one stretch. It can go to 1,500 miles or kilometers. So that is the advantage that we're talking about. And that can only be driven by such futuristic ideas. One of them is the multifunctional composites. Okay. So as a conclusion of this first part of the talk is that multifunctional composites do hold the key for future design of airplanes and also helicopters and also drones as well. You know, drones have the similar issue, especially electric drones. You have to recharge it, isn't it? Drones, of course, these days find many applications, including taking videos for wedding ceremony, but it has many other uses too. Yeah, and surveillance, for example, military surveillance, but much more than that. During floods, natural calamities, and so on. For all this, the difficulty is that you need to recharge them. But with these concepts, it's really easy to enhance the range and endurance of drones quite easily. Okay, so the take-home message is that these concepts definitely hold the key for next generation design of airplanes. With that, I give a 5 minutes, not really a break, but if you want to discuss anything, feel free to do that. And I also take this opportunity to tell a couple of things. One is, so I'll be having 2 PhD positions open as well in the next month will be advertised. So if any of you have any interest on, I mean, not you in the sense, not necessarily you, but your connections, your students who have done a master's degree with very good academic credentials, possibly with some good journal publications, feel free to ask them to get in touch, and I'll be happy to consider. Of course, it has to go through the application route, but if any of you have very good credentials in terms of publications and academic track record, feel free to get in touch. And what I can promise is that that PhD studentship is fully funded, meaning all your tuition fees is covered, and you will be given a stipend that is good enough for living in the London. And as the result, you will be joining a research group that is mentored by me, and I have currently 5 PhD students and a postdoctoral fellow working with me on a range of projects on aeronautics, but also other engineering disciplines. Okay, so let us take a 5 minutes break, and then we can start the next topic, which is artificial intelligence for aerospace materials and structures. And if you have any questions, feel free to ask me. Let me stop sharing for a second.
Yeah, thank you for that. Thank you for that information and offer, sir. Hope the session is open for the participants to ask any questions if you have in the topic what he has shared so far. So the session is open for the participants, and we have a question that any results and analysis part is there. It's more interesting.
Oh, okay.
So it's about, I think, that the self-healing cracks.
Okay.
And we do have a question also, sir. What is the how do you incorporate those self-healing agents into that coating? Do you along with the coating, do you incorporate, or
so
do you do that?
So that healing mechanism relies on the healing particles or capsules, and we put them into the coating system during fabrication of the coating. So the coating is basically done by the technique called atmospheric plasma spray. Yeah. So in which you spray the ceramic coating. So we put the particles in the sprayer as well. I mean, sprayer here is not, of course, a simple sprayer. It's more of an air plasma spray, one of the more advanced techniques to spray. So we put the healing particles along with the spray, so that while we spray it, the particles are also embedded into the coating system. Yeah. So if that makes sense.
Is there any idea about the type of that, the agent, about the materials?
So the specific agent is made of molybdenum disilicide, so MOSI2. Okay, and the top coat, the ceramic coating, it's yttria stabilized zirconia. Okay, and in that you have this molybdenum disilicide, MOSI2, and what happens when the crack is formed? This molybdenum disilicide particle will be exposed to the air, and then the silicon in this particle get oxidized because you have oxidizing air at high temperature. Yeah, this silicon forms silicon dioxide, SiO2, commonly called as silica, and this actually expands and fills the crack. Okay, and during operation, this silica, SiO2, reacts with the zirconia layer, which is the coating, and it forms the layer called zircon. And that zircon layer is structurally superior, and it holds the crack together, meaning it heals the crack, thereby the original properties are restored. Okay, so that is the mechanism as a whole, in terms of the material, in terms of how it actually works, and the resulting product that it forms in the crack phases. Okay. Okay.
Yeah, thank you.
Yeah.
And Mr. Nataraj, you may unmute your mic and you can interact with the speaker.
Feel free to talk. That is perfectly fine. Yeah, the coating thickness is usually in the range of 100 to 400 microns. That is the range of thickness that we're talking about. And the type of bonding between ceramic and metals, as I said, it's sprayed at high temperature, and this bond coat layer, which is typically a McCauley alloy, that actually bonds the ceramic and the nickel alloy underneath. That is the bonding mechanism.
Hello, sir.
Yeah, go ahead, Nataraj.
Yeah, thanks for your nice and kind words. Sir, you talked about the futuristic ideas wherein you have proposed a battery as part of fuselage. What is the typical thickness of the battery that you're talking about?
It's okay. If I talk about battery, it's not really a typical battery that we typically see in a car or in any other context. So the battery that I'm talking about is fibrous batteries. So if you want a typical range, you have seen the carbon fibers, right? So the ranges of diameter of a carbon fiber is in microns. So we actually have the range, these battery fibers also in the same range in its dimensions. Okay.
Yeah, thank you, sir.
No worries. Any other questions? We can spend a couple of minutes, because since I'm shifting the topic to a different domain, that's why I'm having this little break.
Hello.
Hi.
Hello, is it audible? I'm Nataraj, sir.
Yeah, hi Nataraj, just go ahead.
Sir, what is the lifespan of the batteries, sir?
Well, so these batteries are inspired from existing batteries too, lithium-ion batteries. So what is the lifetime of lithium-ion batteries? That's a very interesting question for obvious reason, because what if your battery degrades after you put them into the wing and the structure, isn't it? So would you replace your wing and structure? That is not possible, isn't it? So for that, it would be nice to bring in the lifetime of the aircraft itself. How long do you think an airplane would generally fly? Yeah, easily about several tens of years, isn't it? Yeah, a full aircraft lifetime would be easily 50 years, if not more. So the typical existing batteries can be efficient for currently for about 20 years. Okay, so that means the research still needs to be matured to meet the lifetime of the actual airplane that is in operation. Okay, that is why I call it futuristic. I don't say that these concepts can be implemented in the real aircraft tomorrow. Okay, so there is still a lot of R&D that needs to be done, and that is why one of the PhD studentship that I talked about deals with this topic. So in which we try to develop design tools and analysis tools for exactly these type of materials, to characterize the failure, to understand the failure of these materials under such loading conditions. Because now if you have a wing that is made of battery, the loading condition is quite different. Your traditional loads that are coming in from aerodynamics, but on top of it, since you have a battery, it has its own local loading that induce stresses, that induce damage, that deteriorates the material, the battery material. And that in combination with the aerodynamic loads, it does even worse in terms of the degradation. So that is why, so the PhD studentship that I'm talking about, the scholarship, is actually a 3-year scholarship to exactly tackle that, to understand the failure under such multi-physical loadings. Yeah, so that is why I use the word futuristic, not really, let's say, for now. Okay, I hope that makes sense.
Sir, are papers on related topics from your side available online?
Yes, it does. Yeah. Yeah.
Okay.
On this multifunctional material, you may not find a lot of papers because there are a couple of patents that are being filed there, but you might still see some of the conference papers. Yes.
So
But on
one,
digital healing, yes, you would see papers available. Definitely, easily 5 to 10 different papers available from our group and of us, from me as well.
and one more question, sir. What could be the efficiency of the battery?
Yeah, so efficiency is as efficient as your existing lithium-ion batteries.
Okay.
Okay.
And another thing, sir, I have seen in the video like the one wing it is 5 batteries it is covered, and other wing also it is covered 5 batteries. Total 10 batteries it is attached.
Well,
So does it will it not increase the weight of the airplane?
No, see, that is why I said, so we are not attaching batteries in it. We are replacing the existing carbon fibers with battery fibers.
Yeah, of course.
Meaning,
Yeah.
yeah, so you are not adding additional weight and space to the system. You're replacing the existing material with a new material that does more than one function. Okay. The weight penalty is not that large because you're not putting a new battery into it. That would
Yeah.
be similar to carrying a chunk of battery with you in the cabin, isn't it? That is not what you're doing, what we are doing here. Okay.
Okay. Thank you.
Perfect. Yeah. I see one student raised a hand. Yes, please go ahead.
There is a question in the chat box. What about the
aerodynamic performance effects in case of turbine blades loaded? Yeah. So these healing particles that we are talking about are embedded within the coating. So aerodynamics is generally defined. The performance is defined by what you see on the surface, isn't it? The surface profile, the shape affects the aerodynamics. We are not touching that. We are not modifying that because the healing particles are embedded deep within the coating. So you are not changing the blade profile whatsoever at all. Okay, so it does not affect the aerodynamic performance. Yeah, I hope that answers your question.
Any more questions from the participants on the first part of the presentation? The session is open for you for a minute, one more minute. Kindly raise your questions in the first part of the session. I think that's it, sir. We can move on.
Okay, great. So we can move on to the second part. Okay, great. Let me have a sip of tea actually to get some energy. So this is, you can see this glasses. I got it from India. So namor tea kadayil and wine thandadu. Yes. Okay. Hope that is not informal, but I generally do it. Anyways, let us go on to the next topic, which is one of my recent passionate topics for obvious reasons. One of them is it's becoming really popular these days, but more importantly, I try to find effective applications of artificial intelligence for aerospace materials and structures. Okay, let me share the screen. Okay. Can you see the screen or not yet? I guess, right? Okay, it's
Not yet, sir. Not yet.
okay. Can you?
No. Yeah. Now.
Okay, great.
Yeah.
Okay, cool. So the second part of the topic, which I'll try to spend for about we still have until 10:30, right? So let us spend for about 20-25 minutes, and then we can open the floor for questions. Okay, so this part of the talk, which is also my other primary research direction, and the second PhD scholarship that I talked about is on this particular topic. I mean, not necessarily on composite materials, but it is machine learning for structures and materials too. Okay, so what is the motivation for this particular topic is that of course everyone dwells into this particular topic on looking at applying AI, which is also called as informally as machine learning and also deep learning or neural networks and so on. So people have been trying a lot to apply these new techniques for different, let's say, problems in engineering. Some of them very effective, some of them not that effective. But we still explore different opportunities that AI offers. And for your information, you know, AI as a subject has been existing for the last 40, 50 years easily. Yeah. So the word or the word AI has become popular these days, much more popular, for the reason that we have very good computational facilities these days, and we have a very good mechanism to handle data, to record data. Okay, for these two reasons, one is data capturing, the other one is the computational facilities. AI has really become a forerunner in different applications, not only in engineering, but also or more so in other domains such as finance, marketing, social media, and so on. Okay, so anything that you use in your hobby time or free time is somehow related to AI, whether it is Facebook or Google or anything. But the main point here is AI is still not, let's say, entered a lot into engineering disciplines, the core engineering disciplines. Core here, I mean aeronautical, mechanical, civil, electrical engineering. Okay, and one of the research that I've been doing for the past couple of years is try to utilize usefully, I underline this word usefully, and the next word effectively, yeah, for materials problems, materials and structural problems. And one of the direction that I took during the start is that what you see in this particular slide. So on the top, you have microstructural images. Okay, and it could be composite, it could be metallic alloys or whatsoever, but those are all microstructural images of materials. Okay, and the single line idea of this particular research is by looking at the image of any material, can I tell the properties of the material? Can I directly tell the properties of the material? And what do I mean by properties? I mean the stiffness, the elastic properties, yeah, the shear modulus, the Young's modulus, the strength, the yield strength, the fracture toughness. So I'm talking about all these, but also all these properties would take extensive amount of time to characterize through experiments. Yeah. So if you want to measure Young's modulus, you know what to do. You go to the universal tensile testing machine, you make a sample of the material that you want, and then you test it. You get the stress strain curve. You measure the Young's modulus and the yield strength and the yield evolution if it is metal, or if it is composite, you measure the fracture strength. Yeah. So that is the usual case. But then if it is a composite material, you just do not have one property, but you have, because your material is inherently anisotropic, you have multiple properties, isn't it? Which means you need more than one test to characterize the material. Yeah. So which means the amount of time not only in testing, but also the cost involved in the testing and the cost involved in making the material, different samples, it skyrockets. Okay. So what can we do? can we use machine learning or artificial intelligence to replace the testing, by just looking at the images of the material? So almost any lab have an optical microscope, if not the scanning electron microscope. You look into it, you take an image, you feed it to your AI algorithm, and then the AI can give the properties. So that is the fundamental explorative idea of this particular research. Okay, the answer in short, yes, it is possible. Okay, and what is the primary motive for this particular objective of getting the properties directly from the microstructural images? So if you look at any typical material development workflow, it starts with the requirements, the end requirements of the structure with which the material is going to be made. So it starts with the synthesis. You choose the method of synthesis, the equipment that are needed, the processing condition in terms of the pressure, temperature, environmental conditions, and so on. And once you synthesize it, you actually get the resulting microstructure. So the microstructure that you currently see is a transverse, the cross-section of a fiber composite. A glass fiber composite is what you see, but it can be any microstructure. So after synthesis, you get a microstructure. And after that, you characterize the resulting material for its properties. And properties can be any: stiffness, strength, toughness, fatigue, thermal properties, and so on. Okay, so this is a typical development workflow. And if you see that the property is not enough, if it doesn't satisfy the requirements, you go back to the process and you repeat the cycle. You change your manufacturing method or your equipment, your processing condition, and then you arrive at certain material, resulting material. You have the microstructure and you test it to see if you achieve the required properties. And that is a time-consuming process. It's an iterative process. Okay, so that is why what we wanted is and that is part of the optimization of material development. Okay, so what we do is that to replace experiments, typically we use numerical methods, computational finite element analysis, to get the properties from the microstructure, and we typically call them as multi-scale homogenization. If you are aware of that particular term, I'm sure many of you would do, but that is expensive. Okay, and for that, for doing this optimization process, in order to accelerate the material development, we need a reduced order strategy, and that is where data-driven machine learning technique come in. And that is part of this, the core part of this project. And what we do, the outline is here. We generate thousands of microstructures of composite materials. Okay, and then we conduct finite element analysis using an automated bench. Okay, to get all the properties of our interest. And then once we have the properties and the images, we have the data set that is ready. Okay, and with this data set, we actually train a machine learning algorithm to predict the properties by purely looking at or solely looking at the microstructural images. But there are some intermediate steps. The first step is we quantify the microstructure. Okay, and then we do some dimensionality reduction, which I'll talk a bit into the presentation. And then we use the dimensionally reduced microstructural, let's say, descriptors for training the machine learning model. And in this particular research, we used a technique called gradient booster tree regressor, which is one of the classical machine learning algorithms being used in different applications. And then you validate the model, thereby you complete the loop. So once you finish this, you have a machine learning model that actually gives you the properties by just looking at the microstructural image, and that is it. Okay, so going in detail about the microstructure generation or each step in this particular process. So on the left, you have an actual microstructure of a composite. On the right, you have the microstructure that we generated using our own code. Because to develop this tool, you cannot manufacture all the materials, isn't it? Because you need to manufacture 1,000 different microstructures. You cannot really manufacture it. That defies the purpose. So what we do, we take a virtual approach in which we generate the microstructure synthetically using computers, but we make sure we mimic all the relevant features, the microstructural features from the actual material. Okay, so that is what you see. I mean, from these two pictures, you may not realize that the right is very similar to the left. For that, you need to do a couple of analysis, and that is what you see here in these two pictures. Without spending too much time on this, you see two different parameters which characterizes the microstructure. One is the first neighbor distance, meaning if you take one fiber, where the next fiber is located. Yeah, that is what characterizes, because that is one of the microstructural descriptors. Yeah, and the second one is the orientation of the nearest fiber. Okay, and we do the analysis for both the real microstructure and our own microstructure generated synthetically. You see the red line is the experimental one. The black line, the black nice varying line here is the current one, the algorithm that we generated. Okay, and you see they match reasonably well, both the left and the right, which means you actually capture the experimental or the real features of the material. Okay, and that is good enough to start with. So then once you have a validated algorithm that is able to produce nice realistic images, you move on to the next step. Okay, and we can generate any microstructure of any shapes, any sizes, any volume fraction, as you can see in this particular image, particular slide. Not only in 2D, but you can also do all 3D microstructures in which you only see the particles, but it can be particles of any size or shape, volume fraction. It can also be fibers. Okay, you do not see the matrix because then it would the particles would be invisible if I show the matrix here. But what you can see is that you see RVEs, which are 3D. RVE meaning representative volume element. Okay, great. So with this, we proceed to collect thousands of microstructures. Yeah, we conduct finite element analysis and get the properties. Some of the samples are what you see, but you already saw the samples before, the capability of the microstructure generation. Okay, and these are some data points here. For the first study, we took 1,800 data points, but for now, we have more than 10 to 15,000, if I'm not wrong, around 15,000 microstructures we have together with the properties. Okay, and all these microstructural images, we feed them to finite element analysis, which is an automated framework that we have. And we have certain assumptions on the material properties. Obviously, fibers are linear elastic, we assume, and we take the properties of a glass fiber for now. And then the matrix, we assume it to be elastic and plastic. Yeah, with and we do 2D analysis for this particular research, but of course we extend this for 3D as well in the current work that is being done. Okay, and then we look at different loading cases possible. Yeah, tension, compression, and also shear that you can see in different directions. And we extract the properties that are Young's modulus in 2 directions, 3 directions, shear modulus, yield strength in 2 directions, and yield strength in 3 directions. Okay, for this pilot exercise, we consider these 5 properties as the properties of the material. Yeah, Young's modulus, shear modulus, and yield strength. Okay, so those are the output that you seek, and the input is the microstructural image. Okay, so now what you have is the data set. So data set, if I say data set, it basically means the input-output combination. And in this problem, the input are all the different or the thousands of microstructural images. The output is all these properties. Now, what do we do with this? Now we choose and design a machine learning model that can be trained on this data set, meaning it should learn how the microstructural features are influencing the properties. Okay. So that is the purpose of a machine learning model, to learn these correlations between the features and the properties. Okay, and before that, there are 2 different machine learning tools that we developed. One is based on classical machine learning, which works on a data set that has to do with numbers and numbers, meaning the inputs have to be numbers and the outputs have to be numbers. Okay, it doesn't work with images. So for that, what we do a little pre-processing. you can call it data processing or image processing, in which we use the so-called two-point correlation function. Okay, and then you take a microstructure and then you discretize it, yeah, and then you apply or calculate the two-point correlation function, which is essentially characterizing the microstructure. Okay, and once you discretize it, you basically take a little vector of size r of different sizes from one point to the other, yeah, in which you change the magnitude as well as orientation, and then you characterize the microstructure. In the end, you get a pixelated image that you see on the right, and that is basically a set of numbers. You can imagine that as a matrix, okay, a spatially located matrix, and the highest value is actually the volume fraction of what? Of the particles. Okay, if I go to the next slide, it will be even more clearer. So this is the microstructure on the left. The right is the two-point correlation function plotted. Okay, the peak value is 0.2. That 0.2 is nothing but 20%, and 20% is basically the volume fraction that you see on the left. Okay, and another example, which is for higher volume fraction, that is 60%. The two-point correlation function is basically what you see on the bottom right. Okay, again, the peak value is the volume fraction, that is 60%. But what is important to remember here or to understand here is that this two-point correlation function basically represent your microstructure. And why are we doing it? Because the machine learning algorithm cannot read the image directly. Okay, the machine learning algorithm that we currently choose, because it works with numbers and numbers. Okay, it's a regression algorithm. Okay, so now with this, these two right images are a bunch of numbers expressed in a matrix form, if you want. And that is quite confusing for the machine learning model, isn't it? Yeah. So for that, what we do one more step, which is what called as dimensionality reduction. Yeah. And here we use a principal component analysis. And what does it mean is that, to give a quick understanding, you might have studied about eigenvalue problems, isn't it? So if you have a matrix of size 10 by 10, fully populated, you can convert them to a different coordinate system, whereby your matrix would be a pure diagonal matrix. Okay, your eigenvalues, and that matrix, your matrix with eigenvalues in the diagonal, rest of the off-diagonal elements being 0, they still represent the original system, isn't it? So it's the same thing. So in here, instead of having a matrix which is of size 400 by 400, meaning we divide each image into 400 by 400 pixels, which means the size of the image would be 160,000. Okay, and that is your number of input variables for the machine learning model, which is quite complicated, yeah, for one image. So what we do is that we use the dimensionality reduction using principal component analysis, and we obtain a set of reduced numbers that represent the actual image. Okay, and that is what is principal component analysis. And so you see some of the results of the principal component analysis. And the beauty here is representing a system using its eigenvalues is much more efficient, because it captures all the ingredients with limited number of data, yeah, limited number of numbers basically. So what you see here, I plotted the principal component 1 versus 2, and what you can see on the left is basically you see different islands of these dots, different colored dots. Each of them, they are clustered by themselves according to the volume fractions and according to the fiber diameters, as you see on the right. Okay, so which means these principal components actually captures the necessary details in the microstructure. It does not lose anything. Okay, for example, the first principal component tracks the fiber volume fraction. The second might track the fiber diameter. The third might tracks the fiber distribution, or the spacing between the fibers, and so on. And if you go to the higher and higher order, the meaning may not be obvious, but it still characterizes some of the microstructural features. It's similar to your vibration analysis. The first fundamental frequency is the dominant, isn't it? Yeah, and then you have many modes: bending modes, torsional modes, extensional modes, and so on. But if you go to for a beam or for a plate, you can ideally or theoretically you have infinite number of degrees of freedom, meaning infinite number of fundamental natural frequencies. Yeah, but you do not take them for your design, isn't it? You may take up to first 10 frequencies. But if you want to know the meaning of the 20th or 30th frequency, it may not be as obvious, but it still has some of the details of your structure. Same thing here applies. Okay, the first frequencies would be more dominant in deciding in defining the microstructure, but the later principal components may not be as important. But we still take the first 50 principal components for the machine learning training. Okay, sorry, first 200 principal components for the machine learning training. Okay, and then we go to the actual machine learning model, which is a gradient boosted regression model. And we use so-called tenfold cross-validation, which is a way to generalize your model and test the accuracy of the model and in terms of generalizing it. And after a set of hyperparameter tuning, meaning optimizing your machine learning model for better learning, you have the results here. Once your model is trained, you have the results, as you can see in the bottom. What you have to understand here is that the x-axis is the actual values of the property derived from finite element simulation, or it can come from experiments. On the y-axis, you have the predictions from the machine learning model. And if the accuracy is 100%, then all the data points or all the predictions from the machine learning should lie along the 45-degree line. Okay, but as you can see, all of them are aligned very close to the on the 45-degree line or very close to the 45-degree line, which means the accuracy is quite impressive. Okay, for these elastic properties, the Young's modulus and the shear modulus. Of course, we have the yield strength as well, which is quite nonlinear, isn't it? Yield strength has to do with failure. Yeah, that's nonlinear. You can see even there, though the property is nonlinear, which means the correlations is nonlinear, the machine learning model is able to capture the properties really well. Yeah, so we got excellent predictions. The accuracy is not 100%, but that is not the purpose, isn't it? Even if we get 90 to 95% accuracy, that is really good enough. But the main takeaway here is the computational effort. So to get all these properties, we need to conduct finite element analysis, nonlinear, yeah, in a multi-scale framework that would take a couple of hours easily. And if you want to do experiments, I don't have to tell you. You need to manufacture the material, test it, and get the properties. So we are talking about seconds if you use a machine learning model, yeah, in which you just feed them image, and the model gives the properties. Okay, and this research has been published in Nature Scientific Reports a couple of years back, and for obvious reasons, this was rated as top 100 throughout the materials engineering domain for that particular year, 2019-20. Okay, of course, we have some validation, but considering the time, let me. Okay, this is again validation, which shows basically the capability of the model to predict the properties on unseen images. Yeah, so here we feed the machine learning model with images that are structured, regular arrays of fibers. But even there, the model is able to predict the properties really well with 97% accuracy. Yeah. For some properties, the accuracy is even 99.9%. Okay. The other thing which is really important is, of course, you can, if you have a data, you can train and develop a machine learning model on anything, literally, isn't it? Yeah, that's quite easy. Yeah, because you have several open source literature available, codes available. You can always do it. But as engineer, as a researcher, as an academic, what you really need to know, what you need to be aware is what is the additional contribution that you make to the scientific community is what is important. Yeah. So, and one of them is basically this inference, what you get out of it. So here, what we do, we not only train the models and predict the properties, which is of course useful, but we also understand how the machine learning model works. What is it really doing? How it is learning? How it is correlating between the microstructural features and the properties. Yeah. So that is this little study in which you see the different principal components and how they are influencing the predictions of the machine learning model. And as you can obviously see, the first principal component is the major contributor to the predictions, but also the further principal components do contribute. And interestingly, the first principal component is actually the volume fraction, obviously, which definitely dominates the predictions, no doubt about it. Yeah, that's the first order effect. How many fibers do you have in the composite? Definitely. But then you see the third and the fourth principal component somehow tries to understand how the fibers are oriented. Yeah. So you see I've plotted the third and the fourth principal component, and they peak, not the maximum peak, but they have their own local peaks. Okay. So they have influence by telling the machine learning algorithm, or in other words, the machine learning algorithm learns how the fibers are oriented and which element in the horizontal direction. Okay, so these are the additional physics that we can actually derive by digging into the black box, which is the machine learning. Yeah. Okay. Now the second research that is currently under review is, instead of using a classical machine learning algorithm, we want to eliminate the need for the pre-processing of the image. What we need to do is that we want to provide the image directly as output. I'll finish in a couple of minutes. We want to directly feed the image into the network, into the deep learning tool, and then get the properties directly as outputs. Yeah, that is what we did here, in which we don't have to do the 2-point correlation function. We don't have to do the principal component analysis. Your deep learning tool or algorithm directly takes in images and it spills the properties. Okay. Without going into detail, it's basically the fully connected neural network that we used, but we also used a convolutional neural network too. And here are the predictions. Neural networks are shown to be predicting better than the machine learning algorithm that we developed earlier, because the accuracy was about 98 to 99%, both for the elastic properties, but also in the next slide you will see the CNN, the bottom picture, the bottom result obtained from the convolutional neural network. They predict really well the properties. The accuracy is easily close to 99%. Whereas the top model, that is fully connected network, the accuracy is not that much because it's a fully connected network. Okay, meaning the learning is not as effective as the convolutional neural network, especially for the nonlinear property, which is the yield strength. Okay, so I'll spend a minute or two on this particular one, which is interpretability. Why is this important? Because, as I said before, anyone can develop a machine learning model if you have a nice data. What is really important as an academic, as a researcher, is that you need to understand what is really going on in the black box. Yeah, because any AI, machine learning, deep learning is always considered to be a black box, isn't it? Yeah, because effectively a machine learning model is an intelligent curve fit. It's an intelligent interpolation function, but in a multidimensional space, which is not that trivial if you use any other classical interpolation or curve fit technique. Okay, so that the machine learning model, or here the deep learning model, a subset of machine learning, is able to extract the important features. For example, the top left is the actual image. The top right is the machine learning model itself detects the matrix phase. The bottom left, it detects the fiber phase. The bottom right detects the interface. We managed to get nice physics out of it, meaning we derived physics from the unphysical AI black box, and that is quite impressive, which is not usually done. And we actually managed to derive physical models for predicting the properties from AI. And that is what you see here, and this little work is under review currently. And we also showcase the applicability of this tool that we developed for real images, isn't it? So far we did virtual testing, but now what you see is the actual micrograph, real material. And we took different chunks of these materials, and then real images, we fed into the model that we developed. And as you can see, the prediction is really good because the accuracy is easily 95%. Okay, in other words, one of the properties that is Young's modulus, the experimental value, the non-dimensionalized value, is 3.63, whereas the predicted value is 3.89 to 87, which is quite impressive because the clarity of the experimental image is really bad. But even then, your AI tool is able to learn and predict the properties reasonably well, and that is a success really. Okay, so what I'm trying to say is that machine learning tools do have the capability, scope to offer within the context of aerospace structures and materials design if used appropriately and effectively. Okay, and in my research group, we do use AI for different techniques. One of my by IMechE, which is the equivalent of Royal Aeronautical Society for Mechanical Engineering, because IMechE do have an aerospace division. So he is sponsored by IMechE for his PhD research, and we develop machine learning tools for health monitoring in aerospace structures. Okay, and another PhD student is working on developing material models, constitutive models, using machine learning. Thereby, you reduce the computational time for simulations by a factor of 10. Yeah, especially for complex simulations, which is quite important for aerospace industry. Because with my experience working with Rolls-Royce, typically a full blade simulation, engine blade simulation, a fan blade even takes about a month to complete. Okay, and imagine if we offer a computational time reduction by a factor of 10, then instead of 30 days, you are doing your simulation in 3 days. And that is the power of AI that we are talking about. Okay, with that, I conclude my talk on this, and I open the floor to questions if that is allowed. Thank you.
Well, thank you very much for this wonderful session, sir. Now I may request the participants to post your questions in the chat box, or else either you can unmute your mic and you can talk to the guest speaker directly.
Hello. Once again, thanks for eye-opening techniques. The AI that you talked about, is it only an image-based? Suppose if the image is not available for some of the parameters, so what would you suggest?
Yeah, so as you can see, we do not necessarily use the experimental images. We create our own images that replicates the experimental images. Okay, and why images? Because the whole idea is that to skip the experimental testing, isn't it? So for that, what is the intermediate thing that you can actually obtain? You manufacture material, and then you can look at the material, isn't it? That is the only easiest thing that you can do. Yeah. So if you can look at the material, not with your eye, but with any simple microscope, you get the image, you feed it to your algorithm, it gives the properties. With that objective, of course, the image is the only possible input. But there is another work that we are currently doing in which we try to skip the image part, in which we start with the synthesis part. What manufacturing technique you use, what processing condition that you use, what are the raw materials that you use. Yeah. But by just based on those different parameters, can we predict the properties? That is even more ambitious, but that is what we are currently starting on, in which you do not even need the images. You just need your starting point, which is your manufacturing technique, your operating temperature, pressure, and so on. Okay. I hope that answers your question.
Yeah. Thanks. Very nice.
Okay. There is another question coming, which is how does AI help in product development for any particular application? Yeah. So one obvious region that AI can help is to accelerate the design process. And here, design process, I'm not talking about the CAD design because that is not design. Yeah, but typically we talk design as CAD design. CAD is not the design. CAD design means everything, starting from preliminary to detailed, intermediate to detailed, which involves computational analysis. So there, it can really accelerate because the tools that you develop based on AI can work really faster without losing accuracy. That is one direction that you can actually accelerate the product development, any product development. The other direction is in manufacturing. Yeah, because any manufacturing of any product, it has a manufacturing line in which there is a lot of inefficiency that are going on. So if you use data-driven approach, utilizing or bringing in machine learning there, you can save significant amount of cost and time there as well. Thereby your product development, especially in the manufacturing point, is also efficient. And there are numerous research that are going on in these two directions. Yeah, which actually part of the product development, not only in aerospace, but
Any standard database available for these applications?
not really, because all these research are still in its initial stage, especially within the core engineering. data set is not openly available for obvious reasons. But what I presume is that in the near future, for example, the next paper that we are writing, we are planning to have the data set published together with the paper too. So in that case, you would be able to have access to that.
Okay, thank you. Okay, thank you, sir. So typically, yeah, we need to generate the data that becomes most important.
So the ideal vision, if you think about it, 20 years down the line, the assumption is that you would have data available. Yeah. So currently we are developing data virtually, but the idea is that in the future, society, meaning society here, the academic and industrial society becomes more and more open, which means the data will be available, which in turn means that you can have machine learning models developed based on those data. Yeah, the ultimate objective is to develop tools that can be really faster and accurate as well. Okay, for which data is really the key, but with the advancement in data storage and data capturing, things would fall in place. Okay, but for now we have to generate our own data. Yes.
Yeah, thanks for the exceptional session, sir. And okay, it was really nice for organizers for bringing you people like you.
Thank you very much. I'm glad that you liked it.
Thank you, sir. And one more question: how AI help in defect diagnosis?
Sorry, come again.
How the AI can be used in diagnosis part for maybe defect diagnosis, something like that.
Yeah, indeed. So that is an active research that I'm currently doing with one of my PhD students is fully dedicated on that. Well, currently there are techniques without AI existing, yeah, to diagnose damage, which could be based on sensors, for example, yeah, piezoelectric sensors or lamb wave diagnosis. There are many different techniques available for health monitoring, yeah, to detect damage in terms of its location, size, and severity, yeah. In that context, what we are trying to do is that can we make diagnosis based on AI in a more simpler way? Why is that? Because imagine you have a large aircraft wing, yeah, and then you want to detect damage anywhere that is happening. So for that, you would ideally need hundreds of sensors, okay? And with the airplane being in operation, meaning it in flight, it vibrates, it generates thousands of signals from different sensors continuously. So which means you would be accumulating gigabytes of data. So you need to process it, understand from the signals of where the damage is and the size of the damage. That is very difficult because it's a multi-dimensional space. Okay, the correlation is not that easy. So that is where we employ AI to work on this huge data set and then try to see if there are any correlation if damage occurs in these signals, in these acquired signals. And we actually have seen that it could be quite powerful, even if there is a small damage, because the sensors can be optimally placed, and the location of the sensors can also be obtained using AI technique too. Yeah, so we do see a lot of scope in this particular direction, in which we can develop an optimal diagnosis technique using AI in combination with sensors.
And one more question from me, sir. Actually, from my understanding, in case if the efficiency of the AI is AI depends on data what we upload means. So how far the results that we produce for this mechanical testing or any kind of analysis, how far it is reliable?
Yeah, exactly. So in terms of reliability, there are two things that you need to make sure, isn't it? One is the accuracy, that's a direct indicator of reliability. The other one is the validation that you do. So validation in what? You develop a model based on a data set that you have. Of course, your model will work well in that data set. But what you need to check is that how your model is working for a data that the model has never seen before. So one of the examples that you saw in the presentation is that we fed an experimental image of low quality that the machine learning model has not seen before, but it still predicted really well. Okay, so those kind of exercise are important to make your model more generalized. Okay, also I have to point out a caveat that the AI model, any AI model, is as accurate as you design. So it depends on the type of data set that you have. because AI is really good at interpolation, multidimensional interpolation, but in terms of extrapolation, it may not be as good as the interpolation. Okay, so AI can facilitate the product development or design or analysis, but it cannot replace the existing tools. Okay, so it always go in parallel. So you should not see these tools as a replacement to physics-based tools that you already have. Rather, you have to see them as an additional helper, a guide that can accelerate the process that we already have. Okay, so that is how we need to use it. In other words, you still have to do experimental testing. Okay, you can't escape. But the thing is, AI can help you to reduce the amount of tests that you want to do. Instead of 100 different tests, you can just do 5 to 10 different tests. Yeah, so that is the scope that I'm talking about. It's not really, I really don't want to see AI as a replacement tool, but more of a facilitating tool. Okay, if that makes sense.
Yes, sir. Thank you.
Okay.
Thank you so much.
Another question is, which programming language is compatible? Well, these days people use Python primarily for machine learning techniques, but many other, even MATLAB has its own machine learning toolbox, deep learning toolbox embedded within MATLAB as well. But I tend to use Python with different libraries available, such as Keras and TensorFlow. Yeah. Okay.
Is there any question from the participants? The session is open for you. Kindly. Yes, Nataraj, you have raised the hand.
Yes, hello, is it audible?
Yeah, very much.
Yes, sir, I have one question is like, you said like the thermal conductivity can be known by using microstructure. How it can be possible?
I mean, it's the same way as knowing the Young's modulus from the image. So because if you think about it, what decides the property? Okay, whether it is thermal conductivity, what is thermal conductivity if you understand, or thermal expansion coefficient? What does it do? It's basically it's a thermomechanical property, isn't it? Yeah.
Yes.
Thermal expansion coefficient. So in a composite, what decides the thermal process? It's the spatial features, right? Where your fibers are, where your matrix are, how they are arranged. Because fibers and matrix have different thermal properties. So as a composite, to get the homogeneous properties, it depends in turn on the spatial features, the volume fraction, the size of the fiber, the arrangement of the fibers. Okay. Now you train your machine learning model by exactly on these features. And
Okay.
then you make the machine learning model to understand how these features are related to the thermal properties. Okay, in the end, that is what it is, isn't it? Because any properties, any mechanical or material properties are related to the microstructure.
Okay.
Yeah.
And one more question, sir. Actually, the simulation part and experimental part is entirely differ. It means like we know we are unable to meet 100% the simulation part when it comes to experimental. So what we have to do to overcome this?
Well, see, I would say experiments are not 100% accurate. Simulations are not 100% accurate. But the thing is, we need both of them to verify your design. Because if you talk about, if you talk to experimentalists, they will know the different, let's say, loopholes in the experiments. Yeah, but people, they tend to believe experiments much more than the computational simulations for obvious reasons. But the thing is, it's always an integrated approach. You can't just go with experiments and you can't just go with computational simulations. So they have to go hand in hand. So you can't design a product based purely on simulations or based purely on experiments. So both of them are needed to go hand in hand. Yeah?
Okay, and the last question, sir. What kind of model that you followed in finite element analysis?
Well, the simulations are conducted in a multi-scale framework based on homogenization, in which we apply periodic boundary conditions and the appropriate constitutive models for the fibers and the matrices to get the resulting effective properties. Yeah. So in terms of the material models, it's an elastoplastic model for the matrix and a simple linear elastic model for the fibers. Okay.
Okay.
And the next part, we actually also model damage, in which we use cohesive elements to simulate cracking in the matrix, as well as in the fiber and the interface.
Yeah, thank you. Thank you. Actually, 4-5 models are there, which regularly people used to follow: Johnson Cook model and then linear model. And this, and then in that contrast, I just asked you.
Okay. Yeah. Yeah.
Thank you. Thank you, sir.
You're welcome.
Thank you for your questions. Any more questions from the participants? Well, if anyone wants the recorded version of this session, the link is available in the chat box. The YouTube link is there. You may anytime you may go and watch the session what we had now.
Okay.
So, is there any other questions? If no, can we conclude the session, sir?
Yeah, sure. Okay, thank you very much again for the invitation, Gopinath. Thank you very much again. And I think I know some of you as well from the names. Good to meet all of you, and also best wishes to all of you in your academic career. And thanks again for the invitation. I hope you enjoyed this.
A few of us were from the park, park alumni, so
Okay.
right. Yeah, okay, sir. And finally, on behalf of the department, I convey my sincerest thanks and gratitude to you for being here and accepting our invitation, despite of your busy schedule and huge time difference. We are here, and thanks for the wonderful session, sir. Definitely, those who are here, got a lot of information, and they have gained a lot of knowledge out of this session. So, thank you for being here, sir. Thank you so much.
Thank you. Thank you very much. Take care and stay safe. Best wishes, all of you.
Yes, yes. Thank you. Thank you so much, participants. The speakers' detail will be shared in the group, WhatsApp group. So